Welcome to the Walton Pi. Today we're going to be talking about limits at infinity. As opposed to infinite limits, these are going to be limits as x approaches either positive or negative infinity. So what does that mean? So a limit at infinity is asking what's the behavior of f of x as x gets close to infinity, or as x grows very large, whereas an infinite limit tells us that the behavior of f of x as x approaches some value a is that f of x is approaching infinity. So those are the subtle differences, but they are important differences between an infinite limit and a limit at infinity. So a limit at infinity is where we have the following situation. F of x is defined on some interval a to infinity, meaning that it's going to be defined for every value bigger than some certain finite number. And so then the limit as x approaches infinity of f of x is equal to L if for any epsilon there is a corresponding big N, where if x is bigger than big N, then the absolute value of f of x minus L is going to be less than epsilon. So how does this differ from a limit at A? So both of them are going to have the same sort of epsilon argument, or the same epsilon neighborhood. So f of x is always going to have to remain within a distance epsilon from our limit value L, whereas in a finite limit, a limit at a finite value, we have 0 is less than absolute value of x minus a is less than delta, meaning we are some distance delta away from our cutoff value a that we're looking to see what it's behaving like. But at infinity, we can't say, oh, I'm going to be like 10 away from infinity, because that is not something that we can do. 10 away from infinity is still at infinity. In order to say I am close to infinity, the way we would say that is I am bigger than some very large cutoff value. And so that's what this big N is representing. So for example, let's look at the limit as x approaches infinity of x squared minus 6x plus 3 all over x minus 3 squared. We are trying to figure out, is the limit of that actually equal to 1? So to start off, we're going to say for epsilon bigger than 0, let big N be equal to the square root of 6 over epsilon plus 3. It feels like I pulled this out of a hat, and if I didn't do scratch work beforehand, it would have felt like I was pulling it out of a hat. I'm not going to go through the scratch work. I will go through the scratch work for some limits at infinity in my next video, where we'll go through a couple examples together. But for this one, let's just say n is equal to that. That is some number, and we are going to just let x be bigger than that number. So for x bigger than that number n, absolute value of f of x minus L is equal to the absolute value of x squared minus 6x plus 3 all over x minus 3 squared minus 1. And so now we can substitute for x all the different values that we would have. So the top, x squared minus 6x plus 3, if we plug in big N, well, if we plug in big N, the top just turns into a negative 6. So we get 6 over x minus 3 squared. That's going to be less than 6 over n minus 3 squared, which is equal to 6 over the square root of 6 over epsilon squared, which is equal to epsilon. Yes, that's a bit messy. Don't worry. The examples that we'll do in the next video will be a little bit easier, and you'll see where these numbers are coming from. But for now, this is the process we would have to go through to do it. So because we have successfully shown that for x bigger than that value of n, we have successfully shown that as x goes to infinity of x squared minus 6x plus 3 all over x minus 3 squared is actually equal to 1. I hope this was helpful to understand the concept of limits at infinity. Please check out my next video, where we will go through several examples together so that you'll be able to see the entire process and hopefully understand it a little bit better. Please like and subscribe if you haven't already, and I hope you all have a great day and good luck with the rest of your math.